Good morning, everybody. We will look at how we can use SolidWorks to do simulations from today's onwards. Last few weeks, I discussed about the modeling. I heard that some of you cannot follow the things I did. So basically, as I said from the beginning of the lectures, you need to actively participate on these things, and otherwise, it's not going to be easy when you try to catch the SolidWorks. Especially, I have started from the normal sketches, then I went to modeling like extrusion and revolve. Then we discussed about the reference geometries. Then we went to this mirror tools and other pattern tools. So I I I saw that some of the students don't come regularly to the class. So if you don't come regularly to the class and if you don't do any work at home, there will be problems of modeling the things. So you have to do some work by yourself. It's not a normal regular lecture. Say this is like a practical based session. So you have to enroll in practice. Otherwise, you will not be able to just look at the things and do this. So we have done these kind of models with you. And if you have any questions related to these things, you can always uh, tell me. I will try to do the tutorials again. So a lot of tutorials have been done. Normally, I don't do tutorials like this for the other students in our university. So a lot of tutorials have been done with you because this is an online session. Uh, so you have to do some work by yourself. Uh, these things actually are not difficult. Only thing is you need to practice. It's like driving a vehicle. Without practicing driving, you can't drive a vehicle by just looking at the way someone is driving. So same thing here. So you have to practice and get used to the software. So these things are really important in engineering. So if you know this kind of software, you can say go to a good job. So I this tutorial also I did. So a lot of tutorials have been done. So chapter 9 talks about these kind of exercises I didn't do. So you need to practice these things and get an understanding how we should approach to a question. So these things I didn't do. So if someone wants to do these things with them, I can help. So just let me know if you want to do some tutorials, more tutorials with this because your time in your syllabus it's very difficult to give a lot of time because it's simulation plus modeling both are in one semester. So normally it's split into two semesters in other degrees, but here they have put all the things together, and so you have to do a lot of work by yourself to get through this. So this is again another model I didn't do, but you can try. Say, try it and see. Then you will get a good understanding how this works. So, any questions related to modeling, let me know. I will try to help again. And also, look at our YouTube channel. A lot of tutorials have been done in that channel. I showed it a few weeks ago also. So not only your lessons, the lessons done for the others also are available under SolidWorks. So a lot of SolidWorks lectures are available. So you need to go to these things and check. If you check normal internet or YouTube also, there will be a lot of tutorials. So this is very detailed theory about SolidWorks done for the other students in SLIIT. So we have the mirror but I didn't do these kind of things for you. So this is a very comprehensive note series, and chapter 11 I didn't do. So assembly or those things I didn't do because I don't have time to go through those things. So starting from here, we have done um, some lessons with you. So if you have any questions, just go through these things and follow the lectures. It's not like spoon feeding, so you need to do some work by yourself, get understanding about the software, how it works. Now today I'm going to start simulation area. So because your syllabus is very tight, so we have somewhat completed this area. So we have started with 2D and 2D sketches and went to 3D CAD. We did some solid modeling. Actually, we didn't cover these 5 types export compatibility. So these things actually should learn by yourself. Should you can import files from other third party like step files, IGS files, AutoCAD files, and work on those things. So I basically covered these 2 areas within that 4 weeks of time, 5 weeks of time. So we will now look at how to simulate the things. So they are expecting us to cover a lot in this area also. So they're expecting us to cover uh, structural simulations. So I will start with doing some examples and show you how to do some structural simulations in SolidWorks. Then we have to do fluid simulations also. This is actually a separate subject in normal degree. So when you do a mechanical engineering degree, this is a separate subject. This is a separate subject. This is another separate module. Actually, you have 3 modules in one uh, subject. So they have compressed everything. So then we have to do a lot of work by ourselves to get some understanding about these concepts. So we will look at how to start the simulation. Before we start in the simulation, I will uh, do some theory part. So I don't know your background actually. So that may be another problem when you try when you may not understand or you may not follow the CAD part greatly, because when we do CAD do a lot of manual drawing, then we go to AutoCAD, then we go to the SolidWorks. So actually we have done jump from manual. I think you have done some manual drawing. So we have jumped from manual drawing to SolidWorks. So since we have only 40 hours, so we will look at how to do some basic simulations, not going into very deep, how to apply SolidWorks and do some simulations and get some results. So we will start with the software. So last week I told that we need to have the simulation installed in the computer. We will not straight away go to examples. We will look at the theory first. Why we want to do a simulation. So normally, actually, what is finite element analysis? So this is called finite element analysis simulations. So this is also a very big theory part is there. We will not go behind the theory a lot. We will try to use the computers and show you how to do the simulations in a quick time. So simulation is a numerical technique. That is, it's not an analytical technique. So I hope everyone knows what is a numerical technique. So numerical techniques don't have exact answers. So normally we have approximate answers. So if you just Google this one, numerical modeling is a computer-based method for computing stress, strains, deformation, and flows of complex objects. Usually, this entails discretizing the object into small subvolumes, and as such facilitates the application of the laws of mechanics or structural fluids. So we are going to actually discretize our model. Discretize, the word is discretize the object into small subvolumes, and as such facilities the application of laws of mechanics or for structural fluid. So what we are going to do is simply we have a model. We have a model like this. We are going to simplify our model. Why we do a simplifying is when you see these kind of pillars. these fillets are actually not needed for our analysis. These are just for safety. But this fillet is needed for our design because it's directly related to the model failure. So you need to have a fillet here, but these edges, other filleted edges will not be very much important. So that is for actually safety of the user. So we can, this is our actual model. So we are going to actually uh, reduce some complexities and get a simplified model like this. Then we are going to apply loads and we are going to apply restraints. So we have to fix the part and we are going to apply some materials to the part. Then we are going to do some structural, thermal, vibration, whatever the simulation you want. And when you apply these conditions, the software will do what? Software will create a mathematical model for that. Using matrices and other equations, they will create a mathematical model. Then the model will be discretized. So this discretization means that the entire CAD model will be converted to a finite element model. So we will have small elements everywhere. So when you have a lot of elements, your answers will be good. So here he is going to apply these fundamental equations to all these elements and solve all the elements one by one. So when he solve all the elements one by one and get the cumulative answer, you can get the FPA result. So there's a numerical solver. So the numerical solver will solve all these elements one by one. This cannot be done manually. It's very time consuming. So we have to depend on the computers. But the theory is there. If you try to do manually, it can be done, but it will take a lot of time. That's why we are using a computer to do that, and we are getting finite element results. So actually, what we do is we use a numerical technique to solve these uh, mechanical engineering problems. So normally we solve mechanical engineering problems using finite element. Under mechanical engineering, you have structural, vibration, thermal. But if you look at civil engineering, we may have fluid. Then if you look at electronic engineering, we may have electromagnetic simulations. So a lot of areas are there. So in our syllabus, we are going to look at basically structural, and we are going to look at fluid. So they have mentioned specifically to look at computer computer based fluid dynamics. So CFD. So we have to look at computational fluid dynamics, and we have to look at structural simulations. So structural simulation. So that's the areas I'm going to look at in these couple of weeks. So this is the design process we are going to follow. So normally, traditionally, people did this kind of a design. Why we go to simulations? Basically to reduce our time and cost. So traditional methods involves doing a design and creating a small prototype. Then based on that prototype, we do some testing, and if the testing is successful, we do the production. But normally this won't happen. So if the testing is not successful, you have to go back to the design stage and do some prototype again and do the testing again, and until the testing okay, we cannot go to the production. So this will take a lot of time in this cycle because we have to actually do a prototyping and we have to test the prototype, and after the verification given, only we have to go to the production. So this will take a lot of time when you use the traditional gut feeling methods. This is actually like gut feeling. So you have to do the design, do the prototype, do some testing, and again fine tune your design, do the prototype again, testing, fine tune, again go back to design, again fine do prototyping, fine tune. So a lot of time will be wasted. So that's why early days people spend a lot of time when it comes to a new product design. So if you talk about the bicycle, uh, normal book cycle, it took on around 200 years to evolve. So because they do the design, they start with small prototype test, again do the test design. Lot of trial and errors have been done to a bicycle. But if you look at the mobile phone, it's only taken 30 or 40 years to evolve to this level. So we do CAD design, circuit designs, everything in the computer, and we apply loads and other things and do a finite element analysis. And if the finite element analysis is not okay, we have to redefine the remodel the CAD design, and get the correct finite element outputs. Then if the finite element model is okay, we directly go to production, prototyping, then testing, then production. So this will save our time a lot because these areas are done within the computer interface environment. So you don't spend a lot of time doing redesigns. So this can be quickly done. That's why we are using computer models to save our time and cost. So the whole idea of learning of finite element analysis to verify our CAD model, but don't think that the finite element model is 100% accurate. So it depends on how you do the design, as well as it depends on how you give your boundary conditions. That is, finite element model answers will depends on the CAD model you do and these constraints you are giving: loads, restraints, materials, type of analysis. So all these are really important plus the CAD model. If all these are okay, only your finite element answers will be okay. So don't trust the computers 100%. So we have to do fine tuning and get the most accurate answer. So computer will only display some results. It's our job to interpret the results and get fine tune our CAD model and get the correct finite element outputs. So that's the difficult part in this one. So doing a CAD model is not difficult. Doing applying these constraints are not difficult. But the difficult thing is how to interpret these results. Why we have red color here? Why we have blue color here? Why we have these kind of color variations here? So what can we do to remove this red color here? So those are the problems which an engineer may get. So that is the human's job. So we have to apply some human knowledge, experience, and try to reduce these stresses somehow. So that's the difficult part in finite element. So interpreting the results will be the difficult part. So in your syllabus also, they have told that determine faults in applications of simulation techniques to evaluate the modeling method data accuracy. So this is the difficult part. How to interpret the simulation results. So we will look at how to interpret these things, and software will only give you some graphs and other plots. So our job is to interpret these things and get the say most optimized model out. So I hope you understood some concepts behind the finite element. So we have done the modeling. Few weeks we have spent on doing some modeling. This is a single part. If you want, you can do it for an assembly. So a lot of parts will be there. So we have different materials, different loading conditions. Then we can do the same techniques for the assemblies also. Now, any questions up to this point? So in this lectures simulation lecture series, I will give you the models. These kind of models I will give. Then we can apply the loading conditions. So in the from the second chapter onwards, I will. I think I shared the notes with you.